All right, so before we can actually start using the technique of Laplace transforms to turn our ordinary differential equations into algebraic ones, which in turn we solve in the Laplace domain and then perform an inverse transformation to get our time domain solution, we need to know what the Laplace transform actually is. How is it actually defined? So here, this is on the definition of the Laplace transform. And keep in mind that the definition itself, at least initially, is going to be very counterintuitive. It's going to look a little bit strange, but again, bear with the strangeness a while. Once you actually see how all the pieces are assembled, you'll see that this new technique is actually going to end up bearing fruit. So suppose that you begin with a time domain function. And let's just call it f of t. So the fact that it is lowercase f is important, and the fact that it is a function of t is important. Now, f could stand for any parameter of interest. It might be a voltage, it might be a current, it might be a power. Uh, all of those are valid here, right? Then the Laplace transform of f, which in terms of notation is written like this. So L is the Laplace transform, and then we actually have the book uses squiggly brackets. Sometimes that's a convention. Sometimes the square brackets are just as good. But here, if you have the cursive L followed by some brackets, and inside you actually have the function f of t. That, by definition, in terms of notation, this is the Laplace transform of f of t. And by definition, it is the integral from 0 to infinity of e to the st times f of t dt. So anytime you happen to have any f of t whatsoever, right, what you do is you're actually going to multiply it by e to the minus st, and then you're actually going to integrate away dt. Now, keep in mind that this integral itself, right, is a, a very special type of integral. And the reason being is that this integral itself, the bounds here are going from 0 to infinity. So if you were to actually integrate once you're given f of t, you would then plug in to your upper bound, t is equal to infinity. At the lower bound, you would plug in t is equal to 0, right? So what ends up happening once you plug in those values of t? Notice the value of t completely disappears, right? However, what will be left over because of the appearance of this value of s, it is going to be a new transform function as essentially as a new variable. T has now disappeared, but it has now been replaced by s. So here, the resulting function, once this operation is carried out, we use the capital letter F to denote this new function. And this new function is a function of s, the new variable that we had in that exponential. Now, the reason we call it capital F is to remind us that this f, which was our original one, and this new f, they are inextricably linked together. Right? Now, there are some issues from time to time when it comes to taking a look at the bounds and even checking to see whether or not for any given function whatsoever, whether or not the Laplace transform actually exists or not. So for these Laplace transforms to exist or even potentially exist, we are going to make a few assumptions. So there are going to be some assumptions regarding the behavior, mathematical behavior of the time domain function f of t. So the assumptions that we're actually going to make is one, that f is a continuous, f of t is continuous. The second is that f of t is piecewise smooth. And the last one is that f of t is of exponential order, right? The last term, the exponential order, means that f of t, if it's actually going to, the Laplace transform is going to exist, f of t must decay in a particular manner. And you'll see where these assumptions actually come into play once we actually start going through some examples and start calculating the Laplace transforms, not only of just some very common functions that you see in differential equations, but also one of the things that you will see is that you can perform the Laplace transform of first derivatives, second derivatives, third derivatives, and fourth derivatives, as well as even things like integrals and whatnot. So we're actually going to split the Laplace transforms into two broad separate categories, and we'll see how to deal with them as we progress through the chapter.